Welcome to The Explainer. Today, we're jumping straight into a massive, invisible world that's operating all around us. You know, when we think about the environment, we usually picture sweeping landscapes, huge oceans, or endless skies. But if you zoom all the way in, past what the naked eye can see, our environment is actually just one magnificent, non-stop chemical reaction. It's a giant lab. We're going to explore the incredibly precise baseline chemistry of our planet, how human activities have kind of thrown a wrench into that delicate balance, and most importantly, how we can use that exact same science to engineer our way out of the problem. Let's get into it. Here is our roadmap for today. First, Earth's essential elements. Second, the water pollution problem. Third, purifying our water supply. Fourth, invisible threats in the air. Fifth, global warming and acid rain. And sixth, chemical solutions for tomorrow.
All right, Part 1, Earth's essential elements.
Okay, let's dive into the actual, specific recipe of clean, dry air. It's a highly tuned chemical baseline. A massive 78% of every single breath you take right now is nitrogen. It's largely unreactive, acting like a safe, stable filler that keeps the whole atmosphere balanced while also being totally crucial for plant life. Then you've got 21% oxygen, which is the absolute sweet spot for life on Earth. Honestly, any more than that and wildfires would just burn out of control. Any less, and well, we couldn't survive. That tiny sliver of a fraction left over, that's just 0.9% argon and a microscopic 0.04% carbon dioxide. This exact delicate ratio is the foundation of a clean atmosphere. And as you might guess, any major deviation from this precise recipe is exactly where our environmental headaches begin. Now, let's think about water for a second. In everyday life, if somebody hands you a glass of pure water, it just means it's clean and safe to drink. But in chemistry, purity is absolute. When chemists say pure water, they mean distilled water, literally just H2O molecules, zero other substances invited to the party. Because it's perfectly pure, it has incredibly predictable physical properties, like a melting point of exactly 0 degrees Celsius and a boiling point of exactly 100 degrees. Tap water, on the flip side, is actually a chemical mixture. It's packed with dissolved salts, minerals, and dissolved oxygen. And while those little impurities are perfectly safe and actually pretty healthy for us, you'd never use tap water in a lab. Why? Because even a microscopic trace of those dissolved minerals can completely react with other chemicals and completely ruin a delicate experiment. Now, what's really interesting is how we can visually prove that water is present using some incredibly precise chemistry. Take anhydrous cobalt-2 chloride paper. Anhydrous basically just means without water. When this paper is completely dry, it's a pale blue. But the literal second a single drop of water hits it, a rapid chemical reaction forces it to change to a vibrant pink. There's also anhydrous copper-2 sulfate, which starts out as a plain, boring white powder. Add a drop of water, boom, it instantly transforms into this rich, brilliant blue. It's just a really beautiful, immediate visual confirmation completely driven by chemical interaction. Which brings us to Part 2, the water pollution problem. So the crucial point here is that human activities are constantly introducing highly disruptive, foreign substances right into that pristine baseline we just talked about. Take agriculture. Heavy rains wash massive amounts of leftover fertilizers, packed with nitrates and phosphates, straight into our rivers. From our cities, untreated sewage dumps harmful microbes that completely hijack aquatic ecosystems. Then there's our everyday plastic waste, which physically breaks down into insoluble debris that lingers for centuries, literally choking out marine life. And we can't forget industrial processes, which leach toxic heavy metals like lead and mercury deep into the water table. These cause severe nervous system damage up and down the food chain. And this brilliantly, or rather terrifyingly, illustrates the domino effect of that pollution. This is an algal bloom. When all those agricultural nitrates and phosphates wash into a waterway, they act like an unnatural superfood. The algae just multiply out of control, creating this thick, impenetrable green blanket across the surface. This blanket aggressively blocks sunlight from reaching the aquatic plants growing down below, so those plants die. Then, as millions of bacteria show up to decompose the dead plants, they suck up vast amounts of the dissolved oxygen in the water. Without that oxygen, the fish literally suffocate. It's a devastating chain reaction, all kicked off by one seemingly simple chemical imbalance. Let's pivot to the fix. Part 3, purifying our water supply. To make raw, untreated water safe enough to flow out of your kitchen tap, it has to survive a genius 4-stage chemical engineering journey. Think of it like a series of increasingly microscopic sieves. Step 1 is sedimentation. The water just sits still in massive tanks, letting the heaviest solid chunks naturally sink to the bottom.
Step 2 is filtration, where we physically force the water through thick beds of fine sand and gravel to trap the smaller, suspended solids. Step 3 is carbon treatment. Here, the water flows over activated carbon, which actually chemically absorbs dissolved organic compounds. This is what strips away any nasty tastes or weird odors. Finally, step 4 is chlorination. We inject carefully measured microdoses of chlorine to hunt down and completely neutralize any lingering bacteria or viruses before the water ever reaches your house.
You can literally trace the physical journey from a raw river all the way to your drinking glass. The water gets pumped into a huge storage reservoir, then flows through wide screens built to catch the big stuff, like twigs and leaves. It moves through precipitators to drop the solids out, then cascades downward through rapid gravity sand filters and glides over those activated carbon granules. And finally, right at the end, it gets that crucial tiny shot of chlorine before resting safely in a covered service reservoir. The water is totally clear, completely clean, and ready for your home. It's an absolute marvel of applied chemistry that we rely on every single day.
Moving from the water back up to the sky. Part 4, Invisible Threats in the Air.
To truly tackle air pollution, we need to know the major players, so let's break down this matrix. First, you have carbon monoxide, created by the incomplete combustion of fuels in things like car engines, and it is highly toxic. Next is methane, heavily released by livestock and rotting landfills. This one is a massively powerful greenhouse gas. Then there are particulates. These are tiny, jagged fragments of soot and dust from exhaust and construction that bury themselves deep into our lungs, causing chronic respiratory issues. And finally, oxides of nitrogen. These are born in the extreme heat inside car engines and are a double threat. They directly cause both corrosive acid rain and that thick, nasty photochemical smog you see hovering over big cities.
Let's actually zoom in on carbon monoxide for a second, because it is the perfect example of how terrifying localized air pollution can be. When fuels burn without enough oxygen, that's incomplete combustion, they pump out CO. You can't see it, you can't smell it, you definitely can't taste it. But when you breathe it in, it aggressively binds to the hemoglobin in your red blood cells way faster than oxygen can. It's literally like a twisted game of molecular musical chairs, and carbon monoxide steals all the seats. It locks oxygen out, drastically dropping your blood's ability to keep your brain and organs alive. It's an immediate, extremely dangerous chemical threat. Let's scale things up to the macro level. Part 5, Global Warming and Acid Rain.
Okay, so before we can talk about global warming, we have to define the greenhouse effect. And here's a massive point of clarification. The greenhouse effect is actually a totally natural, absolutely essential phenomenon. Gases in our atmosphere, primarily CO2 and methane, act a lot like the glass walls of a greenhouse. They let the sun's light shine in, but they stop a bunch of the resulting heat from just escaping right back out into the freezing void of space. Without this natural atmospheric blanket, Earth would be an icy, lifeless rock. The real problem, the severe disruption, happens when we humans pump excessive, unnatural amounts of these gases into the sky. We're turning a perfectly comfortable blanket into a thick, suffocating one, trapping way too much heat and driving rapid climate change.
You can see exactly how the mechanics of this work right here. Those distinct yellow arrows, that's high-energy, short-wavelength sunlight piercing straight through the atmosphere. It hits the Earth's surface, gets absorbed, and warms the planet up. Then the Earth naturally tries to re-emit that energy back out as invisible thermal infrared radiation. That's the red arrows. But here is the chemical catch. That infrared radiation has a much longer wavelength. As it heads back up, the greenhouse gas molecules easily catch it, absorb it, and scatter that heat in all directions, including right back down at us. So the thicker that layer of greenhouse gases gets, the more of that red thermal energy gets trapped, relentlessly dialing up the global thermostat.
And a hotter planet isn't our only macro-scale problem. Take a look at the face of this medieval sculpture. It is practically melted away. This is the direct, highly corrosive result of acid rain. When sulfur dioxide from burning coal and nitrogen oxides from our cars drift up into the clouds, they don't just hang out. They chemically react with the water vapor to form dilute sulfuric and nitric acids. When that acidic rain eventually falls, it systematically eats away at limestone and marble buildings, turns freshwater lakes totally toxic for marine life, and completely strips the vital nutrients right out of forest soils. We are quite literally talking about a destructive chemical reaction raining from the sky.
So we've seen the sheer elegance of nature's baseline. We've seen the profound ways our industrialization has completely disrupted that chemistry, deep in our waters and high in our atmosphere. All of this brings us to a massive, resetting question. Can the very same science of chemistry actually step up and fix what it broke?
Let's find out. Part 6, Chemical Solutions for Tomorrow.
This device is an absolute masterpiece of chemical engineering. It's a catalytic converter, and it's bolted to the exhaust of pretty much every modern car on the road. Inside that metal shell is a delicate ceramic honeycomb. It's shaped like that to maximize surface area, and that vast surface is coated with rare transition metals like platinum and rhodium. When extremely hot, dangerous exhaust gases, like toxic carbon monoxide and smog-producing nitrogen oxides, force their way through that tight honeycomb, a brilliant chemical reaction happens in a fraction of a second. The converter literally rips the oxygen atoms right off the nitrogen oxides to neutralize the carbon monoxide. The result? Those intensely harmful gases exit the tailpipe as totally normal, harmless nitrogen gas and carbon dioxide. It is applied chemistry at its finest. But look, engineering a better car exhaust is just one piece of the puzzle. We have to deploy much larger global strategies. That means transitioning away from burning fossil fuels and massively scaling up renewables like solar and wind. It means aggressively looking into hydrogen fuels, which are amazingly dense and powerful, and their only combustion byproduct is pure water, literally just water. For the fossil fuels we're still using right now, we can install flue gas desulfurization scrubbers deep inside smokestacks to chemically neutralize sulfur dioxide before it even hits the clouds. And of course, we can always rely on nature's own unparalleled technology by globally planting millions of trees.
Speaking of trees, let's just take a second to marvel at nature's ultimate carbon-scrubbing equation, photosynthesis. 6 molecules of carbon dioxide plus 6 molecules of water, powered by incoming sunlight and green chlorophyll, flawlessly react to create a molecule of glucose and 6 molecules of pure, breathable oxygen. It is, without a doubt, the most elegant, highly efficient carbon capture technology that exists. Every single tree we plant is basically a tiny, completely solar-powered chemical factory, actively sucking problematic greenhouse gases right out of the air and restoring the planet's baseline.
Well, we have covered a tremendous amount of ground in this explainer. We started with the pristine chemical baselines of our air and water, waded through the harsh realities of human pollution, and finally looked at the incredibly powerful chemical solutions we have right at our fingertips. Understanding the exact chemical mechanisms driving our environment is absolutely the crucial first step. But using that very same chemistry to heal it, that is our next great challenge. The tools, the equations, and the sheer engineering power already exist. So I'll leave you with this. Are we ready to implement the science of tomorrow to save the world of today? Thanks for exploring with us, and keep asking the big questions.